with the University. So please welcome. We're looking forward to your presentation. Thanks very much for agreeing to be.
Certainly. All right. Thank you for inviting me. So, and yes, as you've heard, I'm from the United States, so I talk funny. If anybody is struggling to understand my accent, just raise your hand and I'll do my best. So yes, I am now at SANSA just down the road, and I'm happy to talk here. So I'm going to talk about this. If I can get it to go. There we go. This star Betelgeuse, and I will tell you a bit about where to see it and so on in the sky. This is a photograph of the sky, and Betelgeuse is the way it looks here in the southern hemisphere. In the northern hemisphere, it's flipped over. But anyway, it's this bright red star down here. So it is now visible, right? I was going to bring the whole sphere to spin around, but anyway, so I will talk a lot about stars of this kind and how they evolve. And then recently, this star has been kind of mysterious, and there's a lot of ideas about what's going on. And I'll talk about some of them, and then I'll try and summarize. All right. So yes, where is Betelgeuse? That's what it looks like in the northern hemisphere. Of course, here it looks this way. So it's the one down here. Betelgeuse is the brightest star in the constellation of Orion. And so one way to refer to this star is Alpha Orionis. So it's the brightest, so the first letter of the Greek alphabet. Apparently, the name Betelgeuse is from Arabic, meaning the hand of Jahuza. So we sort of, when we think of the picture of Orion, we think of this as a shoulder. So their concept of that constellation must have been hands up, right? So that's kind of interesting. Yes, in the southern hemisphere, it's visible in the summer, so I guess it's disappearing now, mid-September. No, sorry, I still can't get the seasons right. Yes, mid-September to mid-March is when you can see it, so you should be able to see it now. There we go. There's the cat. Okay, so for those of you who are fans of astronomy, you might be familiar with this diagram showing stars. Along the horizontal axis is how hot the star is. So the ones at the O end are very bright, very hot, so they're more blue, whereas the ones at this side are cooler, so they're red. It's sort of like when you are, cranking up the hobs on your electric stove, right? It glows brighter and brighter. And so when it's not so hot, it's more white. And then the vertical axis is how bright the star is intrinsically. So a bright star, a star that is very close to us will look pretty bright. If you move that one farther away, it looks dimmer. And so stars have some internal brightness, and if you figure out how far away they are, you can make this plot. So the band of stars here is called the main sequence. That's where stars spend most of their lives, and the sun is sort of in the middle of this diagram, partly because we designed the diagram from here on Earth, so of course the sun's in the middle, but it's kind of a medium temperature, so a yellow star. You should see by the cat. And the magnitude scale is kind of defined of like, okay, based on the sun. There are also stars in different parts of the diagram, and Betelgeuse is a very bright red star, so it would fall way up there. So how do stars move around on this diagram? I'll talk about shortly, but that's sort of where these two stars fit in the whole zoo of stars. So let's talk a little bit about the sun first, right? That's in theory, the star that we are the most familiar with. So here's the little scale model. They're obviously not to scale for distance, but the relative sizes are correct. The sun is much bigger than any of the planets. The diameter across the sun is about 100 Earths. So if it's 100 times across, then you multiply it times, the volume cube and so on. So it's like 1,000,000 times the diameter or the volume of the Earth. So we have the one big star, and then of course all the little kittens, the different planets. I think there's 9 kittens, right? Pluto, even though it's now a dwarf planet, still a planet, right? We call dwarf humans humans, so dwarf planets are planets. Oh, and if at any point you have a question, don't hesitate to raise your hand, and we can talk about it. Okay, so this is kind of a familiar diagram of, the sun is a little blob here in the middle, and the planets are all circulating around it. If the star Betelgeuse was where our sun is, it would fill the inner solar system all the way out to the orbit of Jupiter. That's how big this star is. And it's orange, not yellow, right? So let's talk about the sun. So the sun has various layers. We've got the core at the center, where all of the nuclear reactions take place. So gravity pulls all the matter in the sun and crushes it all together at the center. And the gravity is so strong that atoms crash into each other and fuse together. So hydrogen atoms, which are the most common kinds of atoms, form together to make deuterium, and then another one to make tritium, and then a fourth one to make helium, right? So producing helium from hydrogen releases a lot of energy because the mass of a helium nucleus is less than 4 times the hydrogens that could make it. So this is what produces the energy that we see it coming out as light. So the energy is produced in the core, and then it sort of works its way out through the radiative zone and eventually into the convection zone. The density has decreased, and it starts to like boil, and material moves up and down. That's what we call convection. It's like when you're heating up water on your stove, at first the heat just moves through conduction, but eventually it gets so big that blobs of water start moving around, and that's the boiling. At the surface of the sun, you can see that boiling. So this is a movie of a zoomed in sun, and you can see the convection cells. So material comes up through the middle and then flows back down through the edges. And this goes on all over the sun. For scale, here's a South Africa. So these convection cells are about the size of South Africa. If you go on the web and you see diagrams, they usually compare it to the size of Texas, which is, I'm not sure who's calling me. Texas is about half the size of South Africa. All right. So what makes a star get bigger? So those nuclear reactions that I talked about that are turning hydrogen into helium, eventually you will use up all of the hydrogen, and then you'll have the core, which is now just helium, and it will contract some more and heat up more. Then new nuclear reactions become available, and as that core gets extra hot, it starts heating up the outer layers in that radiative zone. And so fusion starts to happen there, and it starts expanding. So that outer layer then gets hotter, which causes the convection zone and so on to puff up even more. So that's how, as a star like the sun gets older, the core gets hotter and it puffs up the outer atmosphere. So the sun, right, the surface of it isn't really a surface much. It's sort of where the light comes from, but it's actually a very low density. It's about the density of the air in this room, right? So these big stars are very tenuous, right? But it's an enormous cloud of hot plasma. And what makes a star like Betelgeuse so bright is that it has such a large surface area. So you see light coming from everywhere, right? If you have a bright light, but it's just a tiny little, matchstick or something, it's not nearly as much bright as, not as much light as if you had millions of candles, so on. So there's our friend Betelgeuse. All right, so how do we know that? Right? I'm telling you, this is what happens. But we have to figure that out somehow. So the main way that we learn about the evolution of stars is we have to find a special case where we can look at a bunch of stars that are the same distance from us and are the same age. So luckily, there are such things, these globular clusters. So this cluster of stars all formed at the same time, and they're all a big blob, so they're kind of the same distance from us. So if you look at that first diagram, the temperature brightness relationship for just the stars in a globular cluster, it looks a lot different than the one I showed you at first. So you can still see the main sequence here, but at some point it ends, and then looks like they travel up here. So what happens is the bright stars start moving to cooler temperatures and brighter. And as the cluster ages, cooler and cooler stars start evolving up here. So that's what, looking at many clusters and doing models of everything, this is how we understand what happens as stars get old. All right, so a quick summary. So the star is bright and it's red. As you heard, it's about 650 light years away, which means that the reason that it's bright is because the reason that it looks bright is because it is bright, right? It's not just that it's kind of a normal star that's really close to us. It is very bright. The fact that it's red instead of blue means that it's cool. So it's a lower temperature than the sun, but a star that is bright and cool means that it is a large star near the end of its life. So that's how we know that. All right. So what's been going on? What's the mystery about? So the thing that brought this star back into the news recently, a few years ago, right before COVID, we observed this star, see how bright it is. Then there's a gap as it goes, out of our view, right? We can only see it during the summer. So in the winter, there's going to be gaps where it's behind the sun. So it does have some variations, over the year and so on. But then this in 2018, it started to get a little dimmer than usual, and then the next year it was even lower. And at the beginning of 2020. It was half as bright as it had been before. And so everybody's like, whoa, what's going on here? Is there's something going on where the core suddenly paused and is gonna, explode or something like that? That was a lot of what people were saying, like, oh, is this star about to explode? Are we gonna get to see this huge supernova in our sky? And then you say, well, is it possible? Can stars explode? So the answer, of course, is yes. Stars can explode. And when a star explodes, we call it a nova because it looked like there was a new star there. And if it's a big explosion, we call it a supernova, right? Astronomers always have such clever names for these things, right? So here's an example of a star that blew up more than 1,000 years ago, right? In about the year 1000, this star, which is now known as the Crab Nebula, was very bright for several months, and then afterwards left this behind. So this is there's something still at the center, like a white dwarf or something that's illuminating the cloud of plasma that used to be the star. So star like Betelgeuse, right? Gravity at the core is very strong. Energy production at the core pushes the envelope of the star back out. You know, there's a balance there. But if gravity suddenly starts overcoming the outward pressure, the core can collapse, and all the material from the star, you know, fall inwards to the core, and that produces a whole lot of new nuclear reactions. So suddenly there's a lot of energy, and so much energy that it blows the star apart. So that's what people were thinking. It's like, oh, if it's gotten half as bright as it used to be, is that because the star is collapsing and about to explode? But since then, Betelgeuse has actually returned to its former brightness. So that probably didn't happen. If it had happened, right, that's the whole thing of like 600 light years away means you're seeing it 600 million years ago. So, if it blew up 652 years ago, then we'd see it. But if it's 649 million years ago, we won't see it for a while. So what else could it have been? Could it be space weather, right? Since I'm the research chair in space weather, you knew I was going to bring up space weather. So this is a picture of the sun, and there are all of these blemishes on the sun, right? That's where the magnetic field is very concentrated, and it's inhibiting the convection, the flow of material that makes these nice convection cells. So if it's resisting that flow, there's less energy coming out there, right? The hot stuff from below can't get to the surface as easily. So it's cooler, so therefore it's darker, right? So these sunspots, they're a few hundred degrees cooler than the rest of the sun, but by comparison, they look very dark. And so what if Betelgeuse was suddenly covered in star spots? That, I guess, could happen. Oh, I guess I was turning on that little animation. You never know when those cats are going to show up. On the sun, when we get lots of sunspots, it reduces the total amount of light coming from the sun. So the astronomers use the word irradiance to be how much light is coming off. And so total solar irradiance is all of the light coming from the sun. So we measure this by just, seeing how much energy is contained in the light. And this is a plot of how much TSI, total solar irradiance, there has been, over the last 20 years or so on. It's 1,361 watts per square meter. And, that's how bright the sun is. And when there are big sunspot groups, it might go down by a little bit. So the long-term change is the solar cycle that I think I talked about last time, right? Some of us remember that long ago, maybe not all of us. So this sort of gentle going down to a minimum and back up, that's the solar cycle. But these big spikes are big sunspot groups that come across the sun. So on the sun, we went from 1361 to 1357, which if we get out our little mental calculators, that's 4 out of 1,300. So way less than 1%, right? 0.5%, right? I don't know. So the sun isn't going to get half as bright just from sunspots. At least it never has had anything like that before. So that makes it a little bit unlikely that Betelgeuse is just covered in spots. There's the sun. So we normally talk about the amount of the sun covered by spots in millionths of the visible disk. So yeah, it's a few millionths. So a few percent of the sun might be covered in spots at any one time, but not the whole thing. All right. So what other kinds of space weather events are, right? And we abbreviate space weather as SWX because regular weather is WX. So the sun does also eject blobs of plasma. We call these coronal mass ejections. So there can be the magnetic field getting twisted up on one of those sunspots, and it can cause reconnection. And it's kind of like breaking a spring suddenly that, you know, releases a whole lot of energy. So we can get big bursts of X-rays, but also big blobs of material. Now, the blobs of material on the sun are not enough to really decrease the brightness of the sun, but you could imagine you know, a different kind of star with a great big dusty circumstellar envelope, or, you know, I could make up all sorts of words. You could imagine that maybe a big burst of material had come out of that star. It would have to be lined up with us, right? You know, if it came out the side, we would never know. So it has to be directly between us and the star for it to block us. But could it happen? Is this a movie? Yeah, there it's going, just very slowly. Okay, there's some movies. All right, here's what it looks like on the sun, right? So we can look at the sun, and if you block out the sun itself, you can see all the gas that's coming out of the sun as the solar wind, and also these mass ejections. So you can see there's something. It's like 1,000,000 times less bright than the sun itself. So that's why you've got to block out the sun. And this observation, so it's just a wide field camera, just with the sun blocked out. It's best if you do this from space, but because then, you know, you don't have the atmosphere scattering light. Another time to observe this really well is during a solar eclipse, which are rare. You got to be in the right spot for them. But you can also do it from a mountaintop. It's not too bad. Depending on how tall the mountain is and so on. And then over here, I thought it was running. Is that not running? Oh, it's just slow. Yeah, sorry, I made that myself. Okay, so here's a tool that we use as a model of the stuff coming out of the sun. This top one, this is looking down. So the center thing is the sun, and these are and this is the Earth over here. And this is the sideways view, so you can see like up and down. And this is a blob of higher density. This is the density, and this is the speed. So we can model these blobs coming off the sun, and you know, figure out, is it going to hit the Earth? People think this is going to hit the Earth. Ooh, it's looking good, or bad in case you don't like coronal mass ejections hitting the Earth. in some other talk, we can do the whole space weather thing of like, what happens when one of these blobs of magnetized plasma hits the Earth, right? The Earth has a nice protective magnetic field, but if you deflect the magnetic field, it induces an electric current that causes power grid failures and all sorts of exciting things. So anyway, so the sun does produce these, and you know, we've never seen anything on the scale that would make the sun be half as bright, but maybe Betelgeuse has something like that. All right, and since I got invited to this because I did my PhD work on this star, I figured I'd show you a few slides from that. Okay, so how do you measure the wind from a star? On the Earth, you know, to measure the sun's wind, we can put a spacecraft out into space and just measure the wind speed going by. But to look at a star 600 million light years away and figure out if it's emitting a wind, what you can do is you can look at the spectrum and look for Doppler shifts, right? Doppler shift is where, like, some, you know, when a car drives by you, it goes zoom, right? As it's coming towards you, the pitch goes up. That is a blue shift. And as it's going away and the pitch goes down, that's a red shift. So by looking at the star and seeing, like, are the spectral features red shifted or blue shifted, right? Red shift means it's coming towards you. No, sorry, red shift means it's going away. Blue shift is it's coming towards you, right? So you can look at a spectral line, and this central reversal might be shifted one way or another. And so it comes out as the two halves of the spectral line. One might be bigger than the other because the absorption moved to one side or the other. Don't worry, there will not be a quiz. You know, but of course it's a little complicated trying to figure out what all the flows in the outer atmosphere of this star are. That's why it took me years. You know, you think like, okay, well, the atoms of this kind come from this height in the atmosphere. So if they're shifted one way, then that must be what direction the flow is right there. But then you find another line from almost the same transition and it's going the other way. And it's like, okay, that made it hard. There's also gas and so on around Betelgeuse. So the word for around a star is circumstellar. And so these two lines are popular in space weather and so on. And then there are absorption lines on top of that from material that's just sort of floating around in space around the star. So that makes it even more complicated. I should have put him up earlier. That's more interesting than the spectra, right? All right. So there have been several ideas before I did my project. This was kind of the idea of the outflows in the outer atmosphere that deep lines form deep in the atmosphere are moving slowly. And then sort of in the middle, it's coming out very quickly. And then the velocity starts to decrease again in the outer atmosphere. It's kind of hard to figure out why things don't pile up there in the middle, but that was the idea. And of course, as an exciting young student, I could draw the little diagram of, you know, it's the material flowing outwards, and then there's lots of motions around from the convection, but then there are like little chimneys where the material flows out smoothly. And that's how you could kind of explain that light coming from the top of this turbulent area would have a different redshift than the material coming out through these chimneys. So, you know, you don't have to know everything. All right, so what else has been going on with Betelgeuse? Is it also changing color? Right, so like, you know, we saw it's like, well, it got dimmer, but has it been changing color? So apparently astronomers from China from 2,000 years ago, they said it was yellow. They didn't say it was red. Ancient Roman astronomers also said that Betelgeuse was the same color as Saturn, right? And if you've seen Saturn in the sky or through a telescope or anything, it's yellow, right? It's not red. Mars is red, right? Saturn isn't. And ancient Greek astronomers, they had lists of stars, and they had a list of red stars, and Betelgeuse isn't on it, right? So clearly 1,000 years ago, or 2,000 years ago, people did not describe it as red. They all said it was yellow. So yeah, what would that mean? How could it have been yellow 1,000 years ago and now it's red? So that motion on that diagram that I said, that takes long time, right? The sun is going to live for 8 billion years. It's like halfway through its life. So, you know, to see something like that within 1,000 years, that would be really strange. It turns out that our understanding of the way the stars move on that HR diagram is, you know, that the bright star up here, then when its core collapses and starts producing different kinds of energy, so it puffs up and gets cooler, right? So it moves to a cooler temperature. But apparently it doesn't just move straight in a steady manner, that it might move back and forth as, you know, it kind of bounces, you know, the core collapse, this part falls back in, goes back to its previous one and bounces. And it might be that we just are lucky enough to see this star bouncing back and forth between the hot and the cool, you know, over a period of 1,000 years, 2,000 years. But if it's going to take 1,000,000 years to like finish that, we are pretty lucky to have caught it right now. It's like, whoa, that's cool. All right, so yes, we're claiming that the shell of burning hydrogen works its way out, heats up those outer layers, but it then essentially cools as the surface area gets bigger. There's the puff. All right, so that's kind of my story of Betelgeuse. So it is a red supergiant star near the end of its life. And we have been watching it for about 2,000 years. It got super dim in 2020. It has since returned to its former glory. And it was yellow just a few thousand years ago. So things are really changing in this star. We don't know for sure which of the ideas that I put out might be happening, but we use our knowledge of the sun that we can study very closely. We can also look at the millions of other stars to kind of figure out, okay, here's an example of this kind of star, and here's an example of that kind. And by comparing different stars and comparing them to the sun, that's how we learn about what's going on with stars. And perhaps more importantly, that's also how we understand what might be going on with our sun. So that's why we call it the solar stellar connection, that we look at stars as examples of what the sun might be doing, right? Because living here on Earth, we think what the sun is doing could be very important. All right. Well, thank you very much. Are there any questions? Yes?
So what's the dominant theory on the reason for the dimming? Was it too unknown? Is it just sort of rather unknown?
Yeah, I think that it is still unknown, really. I think this evolution where it's moving to the red side of the HR diagram, but then kind of drifting back. I think that involves sort of a sporadic starting and stopping of the core, as it kind of peters out a little bit, and then the outer envelope collapses back on. That restarts all of the nuclear burning. So I think that's in general what I understand as the current theory, but I don't think we have a real clear explanation of exactly what would cause that.
It wasn't a coronal mass ejection or burping or cooler.
No, it's very hot plasma, but it's very low density, right? It's very tenuous, right? The surface of the sun that I said, okay, it's like the air in the room, so it's not that dense. But the material in a coronal mass ejection is 1,000,000 times less dense than that. So, I mean, it is sort of like, if you look at a cloud, it is more dense than the air around it, but clouds still are not very dense. But so these blobs of magnetized plasma that come off the sun as the coronal mass ejections, they're low density, but they do carry, they're big, and they carry the magnetic field from the sun. They're all ionized, so you've got these electric charges that grip the magnetic field, so it's frozen into the plasma, and so that's why it carries the magnetic field with it. Yes.
Are you looking at this color from Earth or from space?
So the things over from the ancient Romans and Greeks and Chinese and so on, that's all from the surface. We do have telescopes in space, but this star is actually kind of bright, and so we don't often look at it with those cameras. This data here is from the Hubble Space Telescope. So we did take spectra with it, but there's a whole army of astronomers who always say, no, look at this active galactic nuclei, or look at this thing, or look at that. So it's a lot of competition to look at stars, and convincing telescope committees that I want to see what's happening with this star that did something interesting before. They're like, yeah, next year, maybe. Yes.
Could the giant wedge telescope with its range of frequency possibilities shed any light on the matter?
I believe so. It's very, since it's so bright, it might be too bright to get good measurements. You'd have to do a short exposure and so on. And right now they're looking at lensing galaxies and big, pretty things. So I hope that in the near future they will take observations of Betelgeuse. It's sort of this is where you're a spectrum where you divide up the rainbow into very small increments. And something like the James Webb cameras, they do have different filters, but they're each very broad. But they do go out into the infrared and so on. So you can then see deeper into the star and so on. So I agree that if we can get some observing time on James Webb Space Telescope, that we might learn more about this star. And and yeah, you'd think if it's doing interesting stuff like that, right? Then yeah, let's see it.
There's no link between that date and COVID.
No. That's a good idea, though. Yes?
Your previous slide, I didn't quite understand the two peaks.
Okay.
So can you just repeat the question?
Oh, certainly. Yeah, so the question is about the plots of these spectral lines, and it seems like it's two peaks. So in fact, there is one big spectral line, but then material between you and where that comes from is absorbing the light, but it's very narrow. So it's scattering out the stuff in the center. And if that material is moving towards you, then it's taking out material at a slightly different than the central wavelength. Or if it's falling away from you, it's the other way. And that's why the two peaks don't look the same height, because the absorption got moved over. So it's taking more out of one side than the other. Great question. Yeah, in the back. Oh, yes.
We pronounce it as Betelgeuse, but does anyone ever bother to talk to an arrow? Find out what he actually said.
If I can remember, I think it's Betelgeuse. Yeah, I don't know. We'd have to look on Wikipedia or something. Yeah. Yeah. Yes.
But do we know what stage the star is burning at right now? What element it's burning?
In this sort of state where it's continuously burning, it's fusing helium into higher elements like carbon and nitrogen and oxygen, so on. So that's probably what's going on. But yeah, I know about the spectra. I don't know exactly about the nuclear stuff. Yeah. So the question was, yeah, what is the process currently in the core that's producing energy if all the hydrogen has been used up and the heliums are crashing into each other and so on? You next. Yeah.
My dad always taught me when I was a child that it was Betelgeuse.
Okay. Yeah. Betelgeuse. Yeah. Yes.
Is Betelgeuse a variable star?
Well, yes.
Because is that not an explanation then, or possible explanation for variation?
So it certainly varies on a kind of regular basis on scales of several years or hundreds of years and so on. But the normal fluctuations are maybe 10% or so, rather than the big dip that kind of this dip, which has a period of like about a year, got deeper and deeper and deeper. So yes, by no means is it a stable star, right? All the stars at the ends of their lives, start to wobble like we all do when we walk, right? So yes, it does vary, and those periods of variability have been studied for a long time. It's sometimes interesting to look, back in 2011, they looked at it once in a while, and then it started to look more interesting, and there was suddenly like, ooh, let's look at that star more often. And so there's way more observations as it started to behave in an unusual way. Yes?
If it does eventually explode, can we expect any adverse reactions on Earth from that distance away?
I don't think so. Depending on how much brighter it gets. So it probably, I don't know, how bright do supernovas get? Millions of times brighter than they were. So it's still not going to be as bright as the sun. And it will only be for a short time. But yeah, let's imagine that it got 1 million times brighter. And so it was, at least as bright as the full moon, or maybe it could be as bright as the sun for a year or two. And then it would get dimmer again and leave behind, some nebula. So then you think, well, what would the effect on the climate be if there was all of this light coming in for a few years? Would it have long-term effects? Or would they be transient and, we'd return to our steady state after a few more years? So it's a very interesting question, and I don't think anybody has the answer to that. I can ask my friends who do climate modeling. It's like, what happens if you stick in an extra sun for a few years? What happens to the climate? And they're like, yeah, I don't have a grant to do that. But it is an interesting thing to think about. What would the effect be? It's not like the material from that far away would hit us, right? There's, if you figure out the area of the sphere that's 650 million light years across, and we're this tiny, right? None of that material is going to hit us. And if it did, it's not moving at the speed of light. So if we saw the blast where all the photons get to us at the speed of light, and this other material is moving along at, the speed of the solar wind or something, it's going to take many millions of years more before any of that hits us.
I think the answer has to be no, Charlie. New solar masses, 650 light years away.
650 million.
The effect is going to decrease.
As the square of the distance. Yeah.
No, the answer is no. Only visible away.
Yes.
Another question. You showed us the Crab Nebula. Now, did that happen? How long did that happen? Did that happen in Orion?
Yes, it was in the year 1054. That's when. So the question was, did the Crab Nebula happen recently? So I guess unless you're 2,000 years, 1,000 years old, it wasn't within your lifetime, but it was within the time of recorded records. So in 1054, there was the supernova. That suddenly this new star, I think the Chinese astronomers called it a guest star, that it's just visiting us. So suddenly there was a bright star in the sky, and then I don't remember how long it lasted before it disappeared, but eventually it faded and went away, because the remaining source here in the center is probably what we call a white dwarf. So in that HR diagram, there are the stars here at the bottom, where it's hot but not very bright. So if it's hot but not very bright, it means it's not very big, right? And that's why, so if it's a small hot thing, that doesn't produce as much light as a big hot thing. So we think that there's still some remnant of the star at the center that's lighting up the nebula, but you can't really even see it anymore. And you can see this nebula with binoculars or a small telescope or something, and it's very pretty. So put it as a task. Yes? Do we know the age of Betelgeuse?
That's still intact.
Yes, and the shorter answer is I do not know the answer to that. Although it is true that a star like the sun lives for billions of years. And if this star started out as a hot O star, those only live for a few million years. So they put out a lot of energy, use up all their fuel very quickly. So it's 1% as long as the sun, or 1/10%, maybe less. And so sure, within a few million years, we could guess its age. But then to find it zipping back and forth on the HR diagram, that should pin down its age even more. But I don't know.
I'm just Googled it, 10 million years.
10 million years. Accurate to one significant figure.
10.01 million.
Yes.
You showed us a crab nebula just now.
Uh-huh.
Now, for the life of me, I can't see a crab there. Maybe I'm blind, but I just can't see a crab in that.
Is it because it's in the constellation of crabbiness? I don't know. Why is it the Crab Nebula? You guys are astronomers.
Someday.
Yeah, I don't know off the top of my head why it's called the Crab Nebula, but I imagine is there a crab constellation? There's like 88 constellations. I can't know them all. That's a good question.
I think in the previous sort of days when the telescope weren't quite sharp, the ones we have now, taking image like that, it may be in those days it did look at the crab. I mean, the name is stuck.
Right. No, or right, there's lots of crabs. They don't all look like this one, right? You could look at one of those things that like have been around for like longer than any other. What are those? Yeah, the ones that are just like kind of look like a trilobite. What are those? There's ocean creatures, right? That basically they've never evolved. They look like that. I don't know. So yeah, maybe it looks like one of those, some kind of ray or something. Yeah. Yes.
The fact that it shows up in Sagittarius, that we're kind of in our galaxy, that's the CBD of the activity. And the black hole is in that kind of Sagittarius area, isn't it? Are we affecting the view of it being affected by the fact that what galaxy is it in?
The Betelgeuse, it's in the constellation of Orion.
That's Sagittarius area. No. Where's the black hole of our
In Cygnus, right?
SORCE.
Taurus? I don't know. When I was a kid, the black hole that we all knew about was Cygnus X1. Yes.
The answer to the question where the name comes from, Ross, we have his big telescope on the thing. So it looks like crab leaves.
Okay. Yeah. Okay. So for those on Zoom, the answer to why it's called the Crab Nebula is because someone thought it looked like a crab. Yes.
Have I lost the significance of the cat? The cats.
Everybody likes cats, right? They're everywhere. Yes.
Or any of the images you own.
Not in this talk. But I do have a cat. His name is Helios.
Any of the calls.
No. Someone asked if any of these cats were mine and not in this tag, in this slide package, and none of these cats are named Schrodinger. Yes.
Can you give us assurance that the cats were harmed?
Yes, no cats were harmed. I think this one, someone was trying to treat a skin condition by giving them turmeric or bathing them in. So that's why he's yellow. And no, of course, these palace cats are very happy. And so, yes, and the one where the cat is kind of hanging on for dear life, I actually don't think he's a real cat. And definitely, I guess this orange cat is offended by that other one getting in the way. But yeah, I'm skeptical that it's a real cat.
Any more questions? Okay, I think we
Yes, does, coming from David, Clark Brown, why does something like a prism, a glass prism, manage to divide light, from light into, is it the energy that, take it the shortest route?
Our administration is for
yeah, what's no, no, no. Okay, we would talk to people around. Thank you very much. Wonderful. Yeah, why not?
Everybody looks like they.